Hello guys, welcome back to my channel Gamma Die Gamma once again. Today I bring a special integral that we are going to solve in this video. So let's get started. This was recommended to me and is, I should say, from the book Almost Impossible Integrals by Valean. So the integral is a triple integral as opposed to the usual stuff that we have. It's fractional part of x to the y, x over y. Same with y over z. Same with z over x raised to n dx dy dz. Now, immediately what I want to do is simplify the arguments inside the fractional part because there's a fraction inside the fractional part. So what I want to do is use some variable in place of that. So x over y, we can call that u, which means dx is y du. This kind of substitution is something we're going to do again and again throughout this video. So please get used to it. I'm writing it down now. I may not write it in the future because this is a really long video, or at least going to be. So with this, we just have y integral 0 to 1 over y. We have u y over z, z over uy to the n, du dy dz. Now what I want to do is use this substitution. Before the substitution, what I can do is I can interchange a few things. So I can interchange the order of integrals. So right now we have du, dy, dz. We can have dz, du, dy. As long as the du integral sort of stays before the dy integral. So what I want to do basically is I'm going to, in practice, move the dz integral outside. And the du, dy remain the same. I can't change their order because the bounds of u depend on y, so they have to come before the y integral. Okay, so if I do that, I have y 1 over y, that term, u, everything else is the same. Okay, I'm pointing out that in the textbook solutions, this is done using symmetry, a permutation symmetry in the three variables. I'm going to use this method because I feel this is more complete, and although it is long, I like it. I may do the other method as well, but let's do this first. Now let's introduce this substitution and also change the color. So we have y squared 1 over y 1 over y one over t over u to the n dt du dy. So that's basically changing z and making it a variable of t. Now what I want to do is integration by parts, but you may ask the better question, with respect to what variable? So I will say in y. So that means whenever we integrate, we're going to integrate with respect to y, and when we're going to differentiate, we're going to differentiate with respect to y. So if we write it out, if we integrate with respect to y, and the term we shall integrate is the y squared because that's the easiest, and we shall differentiate these integral, this entire inner integral. Maybe I should mark it. So this is what we're going to differentiate, these two nested integrals, and we're going to differentiate with respect to this thing here. So what we have is, when we integrate, we get y cubed by 3, integral 0 to 1 over y, the rest remains the same. Just recall your integration by parts. Instead of a function, we now have two integrals inside. They're still functions because, we don't really care what's happening inside the integral. The bounds depend on y, and that's all we need. And that makes them functions of y. And then we evaluate this from y equals 1, y equals 0, the original bounds over here. Okay, that's the integral part. And now the derivative part is 1/3 integral 0 to 1 y cubed. We shall have to partial differentiate with respect to both of these guys. So it's a product of two integrals effectively, if you separate them out. So we shall have to use the product rule while we differentiate. I'm just writing it down so that there's no more confusion going on. And we still need to integrate everything. So maybe I should move this over there. dy, perfect. Well, the first term at 1 just simplifies to 1/3, 0 to 1, 0 to 1, u 1 over t, t over u to the n, dt du. Okay, that was easy. And then we have the limit. Now this limit is non-trivial. That's why I'm writing it with the limit definition like that. It's lots of writing in this video, so bear with me. You can skip ahead if you want. I mean, I myself skip ahead when I'm watching again. Okay, so this integral is what I'm going to call L without the limit part. It's L. And we're going to sort of evaluate this in a later step. Now we have the derivative part. So we have minus 1/3, 0 to 1, y cubed. And let's say we differentiate with respect to the u integral first. So the u integral, which is the outside integral, the integrand really has no dependence directly on the y. So all we have to do is, by Leibniz rule, plug in 1 over y in place of u, and then differentiate 1 over y with respect to y. I'm skipping steps. I'm assuming you know how to differentiate under the integral sign. So in place of u, we have a 1 over y. dt. We have the derivative of the 1 over y, which is negative 1 over y squared, and then the dy integral is still intact. We shall call this integral I1. We shall evaluate it later. And then we did this for the u. Now it's time for the t. A similar treatment. Just plug in 1 over y in place of t instead of u, as we did before. du, negative 1 over y squared. That's the derivative of the upper bound, dy. And this is I2. So what I'm going to do is I'm going to evaluate each of these guys, L, I1, and I2. Let's do L first. For L, I'm just going to use an argument. I'm not going to be super rigorous. So notice the fractional part of some quantity is always between 0 and 1, because it's just the, what comes after, what comes. See, if you have some number 1.23, fractional part of this is going to be 0.23, because it's going to be the number minus the floor of that number, which gives you this 0.23. So that's all you really matter, is what comes after the decimal if you consider the fractional part. And with the same logic, the product of three fractional part terms is still between 0 and 1, even if you raise it to the power n, where n is some integer. Well, it's this follows. This is quite simple to see. Now we know the integrand is bounded, so the integral, if we consider, will just be bounded by the difference of the intervals. So this will just be bounded by the difference of the intervals of integration. So intervals of integration in this case, maybe I should add the differentials. I forgot that part. Apologies. Now, so as I said, the difference of the intervals, there's two intervals. There's one over y minus 0, and there's 1 over y minus 0, because there's a double integral. So it's going to be a product of that, 1 over y squared. So that's bounded. And if you multiply by a y cubed to this entire thing, so like if we multiply by y cubed to everything, then this integral here just becomes L, right? Because L was just this integral times the y cubed over 3 part. Maybe let's divide by that 3. Okay. So when we do that, we still get 0. We get L here, and then this becomes 1/3 y. And now if you take the limit, is y goes to 0. L is just bounded from 0 to 0. So that means L goes to 0 in that limit. So the limit really vanishes, which is nice. And now let's consider integrals I1 and I2. What we've obtained so far is this entire term is gone. Yes. So what I've done is I've written I1 for your convenience. Now I'm going to introduce the variable change. Uy is W, because we want to get rid of these awkward terms like a product or a quotient inside the fractional part. So that means dw is du times y, and that gives us 0 to 1, 0 to 1. W over y, 1 over w, dw dy. Now I want you to notice that the fractional part of y is y minus the floor of y. Now y is only between 0 and 1 because of this integration domain here. It's going from 0 to 1. So the floor of y in that range will always be 0. So it's 0 on 0, 1 always. And we're going to use this again and again. So that means we can just ignore the fractional part for y, and we get y to the n. But we cannot do that for the other terms yet. This is raised to n. dw dy, let's keep that there. Now we have to do a similar kind of thing for I2. So I've written I2 for your convenience again. Now we use the substitution. Py is z again, as I said, getting rid of those, or trying to get rid of those complex terms. We have z 1 over y over z to the n, dz dy, and this with the similar logic from before will just be z to the n. We can drop the fractional part on the z. Y over z to the n dz dy. Fair enough. Now what we can do now is we can just combine all these pieces. You might say we haven't done much, but I'll say let's see. 1/3, 0 to 1, 0 to 1, un, now raised to the power n, dt du, plus let's see, the factor of 1/3, which I actually forgot to write. It was right there. Factor of 1/3 for those I1 and I2. We can just include it here now. So 1/3, basically just the result. Maybe let's, instead of y, let's call it y prime. So you see all these integrals are just identical because you can get from 1 to 2 by just changing a u to a y and changing the t to the w. You can get from the second to the third by just changing y to the z and w to the y prime. So you see all these integrals are indeed equivalent and they're definite integrals, so the variables don't really matter. So all of these we can club to be 3 times just one of them. So 0, 1, 0, 1, un 1 over t, t to the u to the n, du dt. Now we can split this up into two integrals. We can split the inner interval from 0 to t and then t to 1. So we get just this expression again, plus t to 1, same expression again inside. Now I shall call one of them I3 and I4 and the other I4. So I3, I4. Now for I3 what I can do is introduce this substitution. T over u is v. So we get 0 to 1, 1 to infinity, t to the n plus 1, v to the n plus 2. And then dv dt. And now another substitution, v is 1 over s. So we get 0 to 1, 0 to 1, tn plus 1, sn, 1 over t, 1 over s to the n, ds dt. Now we can split this up into two separate integrals, tn plus 1 dn dt 0 to 1 s to the n 1 over s to the n ds. Now, if you remember, we've actually solved these two integrals. These two were special cases of the formula we described. I even wrote the special cases down for n plus 1 comma n and n comma n. So let's just use the results that we have. It's just going to be a product of those things. So we have a zeta of I plus 1. And then 1/2 minus 1 over n plus 1, n plus 2, I plus 1, zeta of I plus 2. That's it. We're done with I3. Selecting a color again is always a tricky affair. I4 is this creature here. Now notice one thing, that T over U is actually between T and 1, because if we sort of look at all the values of U goes from T to 1. So with that we have T over U going from T to 1, and then again we know that T goes from 0 to 1. So effectively T over U is going from 0 to 1. So that means the fractional part of T over U, with using the same argument as before, is just T over U. So we can just simplify things significantly here. So the U to the n goes away, and we have 1 over T to the n du dt. You can integrate the U out, so we get 1 minus T to the n 1 over T to the n dt, and we can split this up into familiar results that we can use from before. That and the other n plus 1 dt, and there we go. We can write this as this difference of results obtained before. So I plus 1 zeta of I plus 2 minus n plus 1 zeta of I plus 1. That's perfect. We can club everything finally together, because I is I1 plus I3. Or sorry, I3 plus I4. Which was just this integral. I'm just going to write it because it's such a big result. I have to move it again a little less space. Is just 1 minus, I'm skipping the algebra to write the final answer, because we basically know the form. We just have to algebraically put it everything together, club all the factors together. And then we have a product of two things. So that's a multiplication with the other sum that I'm writing. And it's such a big result that I need to move again for space. There we go. That should be the answer. So thank you for suggesting this integral. This was kind of painful, probably the longest one I've done in recent times. But there you go. That is the solution. Thanks to Valian and his genius. There's this method and the other one, which uses a symmetry, and you just get the answer directly. Uh, so yeah, thank you for watching, and stay safe. Peace out.